Welcome. This is the lesson number 20 in our training course for building the automated prediction system with Python and Streamlit for stocks. We still in our pipeline are at the train predict file, and last session we completed calculate RSI. And now it's time for training two models, random forest and linear regression. But before moving to that, what I want to recommend you, whenever you'll have a free time, check the medium.com. Here you can see the link, and this is my page. I believe a while ago I created an article of building the Streamlit and Python model for separate random forest and linear regression models. I'm just trying to get those links. So long story short, if you will search in here, you will find dedicated articles for those. Actually, there was a whole project of building the system, but it was like for one time, not for the complete automated system. So here they are. They were published April 2024. So here you can find an explanation of the methods named random forest and linear regression, and have a deep dive on it. So yeah, but now let's move to our coding. Let's have our one-liner here. Train random forest model. And pay attention that it will take as an input the symbol, the X and Y for numpy's array, and it will return random forest regressor. I believe we did that X and Y for preparing features. We will start with declaration of model being random forest regressor, estimators 100 and random state 42. Model fit XY. And after this we are going to save the model. Saving model path, this models directory, random forest, F symbol, and RF. Job library and joblib dump model path and return model. Let's talk a little about the code here. What will random forest do here? It will capture known linear effects. It learns feature interactions automatically. It is robust to outliers, and no scaling is required. We are here starting with a declaration. of non-parametric and non-linear model, which handles the noisy technical indicators and works with lag figures. We are then declaring the model ensemble of the decision trees, if you will. Each tree is trained on a bootstrap sample of the data and a random subset of the features at each split. The N estimators, which is the tree, we are providing enough trees to stabilize predictions. And random state 42, we are doing the results reproducible, and it is critical for debugging and evaluation. And without it, model will change slightly on every run. So this brings the stability. Model fit XY. What happens here? Each tree will recursively split features with close lag being below the threshold, go either left or right on decision trees. Then the forest will average predictions across all trees and cancel out overfitting noise. We then do symbol isolation and setting the model persistence, and this line here persists trained ensemble or a combination of the trees for reuse. And by returning the model, we are allowing immediate downstream usage. And random forest, what it does, actually it answers to questions based on many similar historical patterns, what will usually happen next. So it's rather pattern matching, not extrapolation. Okay, with this complete, let's also work on linear regression. Excuse me. The code for it may seem familiar. We start with declaring that model is linear regression. Then again, we do model fit for X and Y. And then again, saving model path, linear regression, LR joblib dump, model path, and return model. You can see that's pretty similar to the random forest. Let's talk a bit about linear regression. This is training a parameter-based model, establishing a simple and interpretable benchmark. With creating this line, we creating or initiating an ordinary least squares regression model. Each feature is contributed linearly, effects are additive, and no interactions unless explicitly engineered. This brings models to being fast, but also sensitive to multicollinearity and scaling. The model here computes by minimizing the mean squared error, find coefficients that best explain the y as a linear combination of features. Hereby, it assumes that relationship is linear, errors are independent, and features are not basically heavily correlated. Then this saves the model. Basically, we are again dividing with the symbol, because each stack has its own dynamics. We will prevent by this model overriding and per symbol retraining. And the job leap here will dump the data. And why job leap? Because it's faster than others for NumPy heavy objects, and we remember that this is a NumPy object. And this is standard for sklearn models. Returning model, thus it is ready for immediate in-memory use and easier for chaining. Conceptually, what does linear regression do? It answers the question, if the world behaves approximately like it has recently, what price would be reasonable tomorrow? So again, this is based on events that happened already, and based on that make prediction. It uses SMAs, momentum, and short memory flags. Again, the speed of the model, the stable baseline, and often it's surprisingly competitive with more advanced and complicated models. This was all planned for this session. Next, we are going to work on train RMM method. See you at the lesson 21. Bye-bye.